I think I will be starting off. We have a series of 4 short talks followed by a panel discussion. My understanding is these are 10-minute talks, so very, very short, followed by a panel discussion. I will start off and then hand the floor over to Ilana, and Ilana will hand off to John Riefel, and John will hand over to our 4th and final speaker, Giacomo Indiveri. We'll then have a panel discussion, and then we will break at 3:30 p.m. GMT time for a much-needed coffee break. Okay, so let me start out. Can everybody see my screen?
Yes, you can see it.
Okay. So for those of you that don't know me, my name is Josh Bongard. I already see a lot of familiar names and faces on the call here, so it's nice to be back in this community. I'm currently a faculty member here in the University of Vermont, and I'll tell you very briefly about some of our new work on what we refer to as morphological pre-training. You'll see that I have a shameless plug here. We are currently hiring in my group here at the University of Vermont. It's a very beautiful part of the United States if you haven't visited before. We have immediate openings for several postdocs, and I'm also looking to hire some doctoral candidates in spring 2024. So if you fit either of those bills or you know people that do, please send me an email or DM me in the Discord, and happy to follow up with you about that. Okay, so just a little bit of background. A lot of this is all in the family. You just heard from Anil Seth. Back in the Stone Age, I was a master's student at the University of Sussex and took a course with a seminar leader at that time named Anil Seth, and he introduced me to this idea of embodied cognition, and I'm still scratching my head over it 25 years later. After my master's, I went on and joined Rolf Pfeiffer's lab with Fumiya. And after that, Rolf and I wrote this book called How the Body Shapes the Way We Think. And I don't know if Rolf is here on the call, but I'll share a short story with you. When I joined Rolf and we were talking about embodiment, I said, yeah, that's great, but how? How does embodiment shape the way we think? Most of the people on this call probably have an answer to that or an idea about that, but I really pushed Rolf on that, and that sort of has become our Uber question in my group over the years. What exactly is it about embodiment that supports the evolution or development or learning of adaptive, or what we might refer to as intelligent behavior? So where do we look? We look at the body, of course. That's what embodiment means. And there's a lot to go. There's a lot to go looking for. So just for fun here, I'm not an astrophysicist or a cosmologist, but as most of us know, most of the universe is unseen, ununderstood, even hypothesized. I would argue, or I'd like to argue today, that there is a lot of dark matter in the study of human intelligence, despite what Twitter might be telling us in the last 2 weeks. We look at human intelligence, animal intelligence. Anil just spoke very articulately about this. Our focus, however, tends to be at the organism level. What do we, or what does the organism see, sense, and so on? How much video and audio data do you soak up as you transition from the form on the left to the form on the right? But of course, that training data is a very small fraction of the dark matter of sensation and actions that you perform over your lifetime. It's this part of the life cycle, I think, that's really been overlooked. And if you think about it, you start to actually get down into the data. If you think about the size scales that we all have traversed in making it to adult human form, we transition over at least 4 orders of magnitude in terms of length scale from egg to newborn. And our cells collectively have to homeostat. They have to keep us within the range that allows us to survive and thrive. Our cellular collective has to maintain this over 10 orders of magnitude in terms of amount of cells. We start as 10 to the 0 cells, and by the time we're born, we're already a group of 10 to the 10 cells. And it's only the last 4 orders of magnitude that we in machine learning or robotics or embodied cognition or cognitive science tend to focus on. So if we switch our perception and we try and view the acquisition of intelligent behavior not from the organism level, but from the cell level, think about the breadth of, as Anna was just mentioning, think about the breadth of perceptions and sensation and actions that individual cells or groups of cells need to perform to keep us alive and allow us eventually to survive and thrive. The intelligence, if it's in there, if it's in us anywhere, it's in the cells. The intelligence that we exhibit at the organism level from the point of view of cells, the breadth of environments that we are exposed to as adult humans, that breadth of experience, I would argue, is breathtakingly narrow compared to the breadth of experience that our cells have to grapple with during development. I would argue that that changes the way we think about embodied cognition, or, and in my lab's group, robotics. So we tend to think about what kind of training sets we need to expose our robots to, what kind of video and audio data do they need to be exposed to. A lot of the assumptions behind those questions is, again, we're assuming things at the organism or the overall machine level. I'd invite you to consider this particular machine here. What are you looking at? The darker Pac-Man shaped robot that you see here, this is an adult xenobot. It's a robot that's built from genetically unmodified frog cells. It's about 1 millimeter across, so about the size of a speck of pepper. What you're watching is actually a kinematically self-replicating xenobot. This is a single xenobot parent that is partway through constructing a xenobot child. Those small clumps, those small white spheres that you see there, those are clumps of genetically unmodified frog skin cells. Those cells are partly sticky, they stick to each other, they also actively connect to one another. So you're watching the birth of a new kind of robot, and it doesn't make sense, particularly at this point in time, to talk about that robot, that child xenobot, at the organism level. It is the cells that are sensing and acting within the clumps that are eventually going to form the child xenobot, and also between the adult xenobot. So that experience, the experiences that those cells have, they have been having those experiences not just for a few minutes or a few hours in this petri dish. Cells have been having that experience, having to grapple with changes in sensation and having to act accordingly for 3.5 billion years. They are the intelligent machines, not the machines that they construct. So in order to switch our viewpoint as a community from the whole machine or the whole organism level to the cell or the component view, I think the xenobots in the emerging field of biobotics in general helps us in making that perceptual transition. Rolf was also very fond of saying when I worked with him, if you really understand something, you understand it by building it. We now, thanks to synthetic biology and its connections to AI, we can task an AI, we can challenge an AI to construct, to build new kinds of organisms and new kind of machines for us. And we can watch that process in its entirety. And I think that will give us new views onto this idea of morphological pre-training. What kinds of experiences do cells or components have that pre-train them to deal with a surprise at the organism level? What you're looking at now is another xenobot. This is from a different experiment where our microsurgeon, Doug Blackiston, is reaching in with micro utensils and cutting the xenobot almost in half. And it's exhibiting amazing zero-shot learning. It's recovering from that injury over a few hours without ever having experienced this particular insult of cutting before. That's true of the organism. The organism has never experienced this, what looks like a surprising event from our perspective. But think about the cells as they were self-organizing into this xenobot. Think about the breadth of sensory and actuation experiences that those cells had during the construction process. What the cells are experiencing during this insult is probably not that surprising to them. it's just an example of what happens when we shift our view. We're now in the process of taking some of these ideas of what we're learning about how cells communicate and how they self-organize from the xenobots and from the biobots project, and feeding that back into our construction of machines. I'll finish with this slide and then turn over the floor to Ilana. What are you looking at here? You're looking at some very recent work from one of my PhD students, Caitlin Grasso. These are minimal machines. These are neural cellular automata. We have tasked these machines with homeostating, growing and fitting inside and not outside these green squares. The neural cellular automata that you see in the top half of the screen, we've used a standard optimization process to train them to stay inside the green square, and you can see they're not doing a very good job at doing it. The neural cellular automata that you see in the lower half were also trained to homeostat and stay within the green box. They were also tasked with doing it in a way where they communicate, the cells in the cellular automata should communicate with each other in ways similar to the ways that we see the cells in the xenobots communicating with one another as they self-assemble and try and homeostat. So just an example of sort of, I think, what's coming for AI in general and embodied cognition in general. We have a whole new set of tools that allow us to learn by building new kinds of machines and feed that back into the construction of lots of other kinds of machines. Okay, I think I will stop there and I will forego taking any questions. I think the idea is for us to take questions at the end of the session. So Ilana, the floor is all yours.